All right, so I'll talk a little bit old contaminants, PCBs, and then I move on to newer stuff like PFASs. And there's a bunch of co-authors. There's Tao Sin, let's see. There's some of my students, Tao Sin, Carrie, Houston is a visiting scientist, Dave is my lab manager, but then also groups we work with. Alfred Wegener Institute, I'll point them out as we move along for deployments in the oceans, Environment Canada for Arctic work, and then more recently groups from Örebro, Toronto, and Harvard with whom I work on perfluorinated contaminants. So initially I thought I'll start with organic pollutants in general and why that is sometimes a global problem. And then I move on to the stuff we used to detect some of these pollutants, in this case passive samplers. We then move into the Arctic because it's nice and cold, go into PFAS, and then come back to where we are right now. So this is a typical graph of the production volume and number of chemicals in industrial production across the world. Basically, it took off after the Second World War. We're looking now at roughly 90,000, 100,000 chemicals produced in any of the major blocks, be that Europe, North America, Japan, or China, a few of which we know enough about to know whether they are really safe. And we certainly have learned over the years that we produced a lot of chemicals that were not safe. And PCBs, polychlorinated biphenyls, might be one of the most famous examples. Early on it was mentioned DDTs. So the PCBs is a wonderful inert group of 2 biphenyl rings with some chlorines. Were used in transformers, caulk, adhesives, ballasts and lamps, in paint, and then in window caulkings. There's 209 different congeners. They're all persistent. And we now know that they shouldn't have been produced, and we continue to have leaks of them into the environment. But how do we actually know that they were a problem? And this is very interesting because it was complete accident. It was a Swedish scientist, Søren Jensen, and he was looking for DDTs in bird blood, because DDT was used, so he thought he might find it. But as he looked at his ECD chromatogram, he realized there were some other peaks, quite a few other peaks that were present other than DDT. And so then he realized, after some further discussion and investigation, that it was PCBs that he found in those birds in Sweden. And he then concluded that this might be the most stable group of organic contaminants in existence, and therefore it poses a threat to life. So he was very insightful and foreseeing, but he was of course wrong. They are not the most stable group. PFASs are much more stable, I'm sorry. But they certainly posed a threat, and we had to ban them afterwards. So the problem with PCBs is of course not that the concentration in the water is great, it's not, but it builds up in the food chain, and then top predators have real problems. And the most famous might be Lula. In case you haven't met her personally, it's too late because she's dead. It is a killer whale who washed ashore on Scotland, I think 2 years ago, and she had roughly 1 per mil of her blubber was PCBs. So roughly 1,000 milligrams per kilogram. That is way above thresholds of safety. Lula was a female, but she never reproduced. The idea is that, of course, she couldn't reproduce because she was basically poisoned by industrial chemicals. And we think that this particular flock or group of killer whales will not be able to reproduce sufficiently to actually exist in a few years. So they'll probably just be gone, because they happen to have the bad luck of living next to the United Kingdom. Something else that happened was these pollutants were not only found where they were used, as in Northern Europe and North America and so on, but they found their way across the entire world. And here is an example of alpha-hexachlorocyclohexane. It's a byproduct. It's the byproduct production of lindane, gamma-HCH. HCH is a wonderfully persistent and effective pesticide, but this byproduct was found to be present in all of the ocean waters of the Atlantic. Fairly low concentration at the equator, which is not a big surprise because nobody lives there. And then a high concentration in the Arctic, which is a surprise because nobody lives there. So that was a bit of a shock. That's 25 years ago by now. How can pollutants reach places where nobody is? They're supposed to be pristine. So then a few smart people put together this idea, and you might have seen that picture or a version of that, the global fractionation idea, the idea that chemicals that are used somewhere will start to move, and their mobility will depend on their physico-chemical properties. And some of them that are highly mobile will actually reach far and remote places like the Arctic. And that could either happen in a series of jumps, which we would call grasshopping, or in 1 or 2 big transport episodes. That doesn't really matter. It could be through the atmosphere or through the oceans. It can be through biological carriers like whales or penguins or birds. And then the compounds will basically get stuck somewhere where they can't move much. And that could be what we call the freezing out in the cold places, like the Arctic. So with these kind of different pieces of evidence together, chemicals that are very persistent, that travel to long range, travel to places, cause effects. Basically, an international treaty was put into place, the Stockholm Convention. That's already now, it was last century, I think. So, and they target anything that's persistent, anything that's bioaccumulate, that has potential for long range transport, so it's an international problem, and then causes some toxic effects. And so initial compounds like dioxins, PCBs were included, a lot of pesticides, DDT, and so on. And then more recently, as the protocol was set up to include any of these chemicals, PBDEs were included later on, and most recently, PFOS has been included, and PFOA is about to be included. And that's maybe a total of 25 chemicals that are globally banned, basically. 25 is a big step, but compared to 100,000 that ought to be screened, it's a fairly small fraction. So we're not quite there yet. But so that's kind of the background. Now I actually want to move on how we do some of the sampling. And traditionally, we looked at the PCBs and the DDTs of the world. They were hydrophobic. And then we used what we call a passive sampling approach, which basically means you put a piece of plastic out into the environment, and then you just don't do anything. You just let it sit. And then diffusion takes place, and over time these pollutants enrich in the passive sampler through diffusion, and then you can calculate the concentration in the environment because you know what's in your polymer, you know something about the partitioning, and you can derive the dissolved gas phase concentration. The beauty is that suddenly we can sample different places at the same time without having to be present at all of them. So these kinds of samplers, it's basically like a plastic bag. We can wrap them in foil, seal them, and ship them out to volunteers, for example. And so this is what happens. Initially, when you put the passive sampler out, it's clean, there's nothing in it, so the new compound of interest will start accumulating, and then finally it'll reach an equilibrium. That's the idea. And at that point, all we need to know is the concentration that we measure in the sampler when we extract it, the density, whether it has equilibrated fully or not, and the partitioning constants. And then what we use, and this is just the mathematical model, it's not that important, is we include reference compounds that are not present in the environment. So we start with a known concentration in the sampler, and we watch their disappearance. So they'll dissipate over time. And now, because uptake and release follows the same kinetics, at any given point that we sample, knowing how much is lost, we can predict the fraction equilibrium reached by the compounds we're interested in. So that way we can use the sampler for really small molecules that might fully equilibrate and fairly big molecules that will not equilibrate, and we can correct for that. So with that said, we thought we'd go to places where humans don't normally go. We wanted to test whether we can use those samplers in the ocean. So we worked together with colleagues in Bremerhaven, the Alfred Wegener Institute. They operate what they call their house garden, and their house garden is at 78 degrees north, so it's basically in the Arctic Circle. And they go there with a ship roughly every year and do all kinds of experiments. So in this case, we prepared passive samplers of different size, put them on these stainless steel wires, put them in this stainless steel mesh, and that was to protect the sampler when they were deployed. Oceanographers are very nice people, and they like to drink, but they're not very careful with their gear. So they basically line it all up on deck and then throw it overboard. So we had to install these tubes just to make sure that they didn't trash everything we gave them. And then if everything goes well, 1 year later they go back out, and if it's really good, they actually find it again. And if they haven't found it, then it's somewhere else. All right, so what we did then is one sampler was here at 25 degrees north, so in the tropics, and the other was there up there at 79 degrees, that's the house garden side. And then we were given distinct points where we could add to the long moorings they have. So this one went down to 2,500 meters, the other only to 1,800 meters. So we had 5 depths at each side. And so the samplers were out for 1 year. And then finally they go back, they find them, they send it back to us, and then student goes to the lab and does all the stuff. And then finally we come out with concentrations. And just to give you some idea, this is obviously trace levels, it's picograms, so 10 to the minus 12 grams per liter. We're looking at between around 1 picogram for all PCBs, 10 for HCB. pH is a little higher. And previous work came up with very similar numbers, so we're very happy to see that our approach seems to work even in the surface ocean. The sampling rate is some idea of how much water was extracted on a daily basis. So it's 5 to 10 liters a day. These were out for a full year. So these passive samplers sample the equivalent of 3,000 to 4,000 liters. That's what makes them so attractive. So we had a total of 2 sites, but that was enough to make some really great statements, so I'll try to do this here. A previous group, a Swedish group, had been on a ship from Sweden all the way to the North Pole, and they sampled PCBs in the water, and then they looked, are there any trends over that distance? So that's roughly 30 degrees latitude, and they were looking whether this fractionation you can actually observe in the ocean. And what they've plotted in the end was a ratio of the presence of PCBs at the North Pole and closest to Sweden. And you can see this ratio changes as a function of vapor pressure, which indeed suggests that there is a fractionation. The more volatile compounds go much further north than the less volatile compounds. As I said, we had a total of 2 sites, and we did the same ratio, and we get a fairly similar plot. So even across the scale of 50 degrees of ocean, we see this fractionation happening. So indeed, the heavier compounds are more present in the tropical sites, and the smaller, lighter compounds are more present in the Arctic. Part of the reason we did that is to make sure that our results made sense, and this seemed to make sense. So we feel confident that we can use this approach to actually get probable numbers and proper numbers. So the other part, of course, now we looked at depth profiles. And so you see everything from surface to 2,500 meters for a range of contaminants. And it's not really that important what the numbers are, but the trends you see basically that we find most compounds throughout the entire ocean. And maybe that shouldn't have been a big surprise, but it was still a bit sobering to realize that we've managed to get our industrial chemicals down to a few thousand meters of ocean. Now, we were not the first to do this. There were exactly 2 previous studies, so I want to show them both. Because the left one here is fascinating, because they didn't use passives. This was 15 years ago. They had built a pump that withstood enough pressure to go down to a few thousand meters. And they found PCBs higher at the surface, less at depth. And the other study by a colleague of mine, Kees Boy, they also used passives, slightly different ones, and they found, similar to what we found, there was some concentration that was fairly high below the surface at 1,000 meters or so, and there were some PCBs further down. So by and large, we felt we're in the same concentration range, we see similar ideas, so it's probably okay. So in case you're an oceanographer, most of you are not, so that's good for you, but I have to pretend I'm one now because of my job. So then, of course, people ask, how are these compounds getting down there? And basically, there's typically only 2 pathways. Either you travel down by particles, or you get down there because the water moves down. Now, the water movement is really slow. The ocean circulation operates on a 1,000-year timescale. And then the only other thing that can limit your transport to depth would be if you get degraded. And so there's 3 hypothetical profiles we set up. You could look a bit like this blue one here. This would be a compound that was very recently introduced. It could be a flame retardant, maybe something else. And you expect concentration would be high at the surface, and then they would just low going down. And if you're very labile, then you won't make it down either because you get degraded. But that's certainly not the profile we saw. Then there's a chance that you get attracted to particles that could be fecal matter from zooplankton, so poop raining down. You could be attached to phytoplankton and fall down with them as they die off. And then at this stage, the bacteria will start chewing up the organic carbon, so they have their lunch, and then they will release the pollutants, so then you would have a subsurface peak. And then the third option is that you just move with the water as a trace of age, and then the peak is just where the maximum production was, and you have to figure out how long the water took to travel down there. I'm not going to go through the details. Basically, we are stuck between, it's probably a mix of the particles and the water mass transport. So this was our initial studies in the deep ocean, and I think the good news for us was we think this approach seems to work. We get reasonable concentration and profiles. Unfortunately, we find the pollutants all through the oceans. Turns out the Atlantic Ocean carries quite a bit of POPs, and how they get down there is for oceanographers to decide, not for us. So just as an example, what I mean by there's a lot, hexachlorobenzene, perfect chemical. I mean, it has everything you need to be really persistent. It's aromatic, it's fully chlorinated, it's also fairly small, so it diffuses fast, so it's probably the best tracer to get something out into the environment. We produced a mere 100,000 tons, of which we think 20,000 tons or so escaped. And if we then look at our profiles from our 2 sites, so always have more than 1, but less than 3, because otherwise life is complicated. If we look at our 2 sites, they're very similar in concentration. And again, these are a few thousand kilometers apart. So we have high concentration around 1,000 meters, and then it kind of drops off. So just for back of the envelope sort of calculation, we said we have a top 1,000 meters concentration around 10 picograms, and the lower few thousand meters is maybe at 5. If you then do the math, we think the Atlantic stores around 2,000 tons, which is probably half of the total HCB we thought is in the oceans. And it's quite a big fraction of the total amount that is somewhere out there right now. So I guess in the big scheme of things, the oceans help us take care of our trash, not just microplastics, also micropollutants. All right, so now that we thought we have this under control, we actually wanted to go a little more into the Arctic. And as you know, we have those 4 elements. There's earth and wind and fire and water. And for the Arctic, relevant are actually only 2 because there's no fire. But we have 2 main pathways to get into that thing. Either things go through the currents in the atmosphere, so the wind, and that certainly was very important initially. That's how the Arctic probably got contaminated so quickly. The alternative is that the ocean moves its water into the Arctic too. That takes a little longer. So we're trying to see whether we can assess that. And just to give an example, this is from the Arctic Monitoring Assessment Program, AMAP. It's a report every few years. This is an example calculation for a-HCH again. And you see there's a big circle. That's the export of HCH from the Arctic through water in the Canadian Arctic. There's another 90 tons here going through the Fram Strait. That's this one. There's loss from volatilization. So for this particular compound, the Arctic is actually relatively oversaturated, so it starts to give things back to us, say, here's some HCH. And so we were trying to figure out whether we can measure something similar for some of the pollutants we're interested in. So in this case, we worked at 2 sites in the Fram Strait. Fram Strait is where the Atlantic Ocean water moves in on the east side, and then it comes back out on the west side with the East Greenland Current. And then we had some surface sites also in the Canadian Arctic. And these 2 sites, again, were depth profiles, same as before. So kind of quickly summarize some ideas. What we see is the PCBs that are in lakes, they have a peak that's roughly in the late spring, and we think that's because that's when the snow melts. So then all the pollutants that were trapped during the winter on snow and ice get released. So we have a pulse. And we also see that lake water has roughly the same concentrations as seawater. So that suggests, again, the atmospheric transport was really important to get PCBs into the Arctic. We also see later in summer that PCBs start being released again from the surface waters into the ocean. Sorry, from the surface water into the atmosphere. And that is by now, I think, fairly well accepted, particularly from other people's work, that as the ice melts and the thing warms up, you have release of contaminants into the atmosphere. And we seem to see the same for the PCBs. But we're interested in the role of the ocean. So these are the 2 profiles, and don't worry about the great details here. This is, eastern side is the inflowing part of the Atlantic water that moves into the Arctic. On the left side is the western, so that's what's coming out of the Arctic. And basically you see very similar profiles and concentrations for both eastern and western side. And the important part is hidden here. That's actually the mass flow of the water. Roughly 7 Sverdrup are moving out of the Arctic, and roughly 9 are moving in. Sverdrup is 1 million cubic meters in a second, so these are major water flows. So, of course, you know what is happening now. We did a multiplication here, concentrations times flow to get the mass. And what we see here is through these 2 points here between Europe and Greenland, HCH is exported through the ocean at around 8 tons. Gamma HCH, similar magnitude. For HCB and DDT, we can't distinguish what's coming in, what's coming out. They seem to be roughly the same order of magnitude. And for PCBs, we think we actually see the Atlantic Ocean pushing more PCBs into the Arctic than is coming out through the water. So there's an import business. All right, so that was all the old contaminants. So Rebecca, if you want to wake up now, we're getting to the new stuff. So PBDEs are already banned, and of course, because we don't look at classes but at chemicals, they had to be replaced. And so what we replaced them with are mostly organophosphate flame retardants. They're just as bad, arguably they might even be worse, but they were thought not to be prone to long-range transport. So Carrie, a student of mine, actually looked at these samplers for these flame retardants, and you see them present at hundreds to thousands of picograms in lakes, in the surface water of the ocean, and concentrations are somewhat similar to what people find when they go out with a pump. And you see the chlorinated compounds are more persistent, so they're higher concentration than the non-chlorinated compounds. So the sad news is we didn't know about these compounds till a few years ago. Their concentrations are much greater than PCBs, and the claim was by the manufacturers that these compounds would not last sufficiently long to undergo long-range transport. I guess we were wrong. And then if you look at the depth profiles, we find them throughout the different parts of the ocean, both in and out of the Arctic. And if you look at the mass balance, the net transport, it's very close to equilibrium. But it seems that we've managed to infuse them on either side of the Farm Strait, so they're in the Arctic and in the Atlantic, and they're happily exchanging. But the good news is the water is flame retardant now. Oh, forgot it doesn't burn. Anyhow. All right, so that's how we looked for some of these legacy hydrophobic pollutants. We find those pollutants in both sides of this Farm Strait. The trade balance is somewhat mixed, and we get some export of the really old contaminants like HCHs. Looks like PCBs we get back in. And now I actually want to switch to what this afternoon session is all about, PFAS. And because I'm the first one, I can give all the background that you'll hear 3 more times later, but then it wasn't my fault. All right, so there is, latest count, 5,000 different chemicals that are somewhat mostly fluorinated. Chemically speaking, they're fascinating because of their particular makeup. They are amphiphilic. They are ionized, they are water repellent, they are dirt repellent. I mean, it's a fantastic invention. If it wasn't for the minor problem that they don't break down, and unfortunately that they also lead to human exposure at quite a vast scale. So we now know that consumer products were probably a major exposure source for all of us. Dust, shouldn't eat it too often, but most of us do because it's somewhat crunchy and tasty. Diet, sometimes, depends on what you eat, but clearly the big one for most people is the drinking water. Either you are heavily contaminated, and then it's a big problem, or average people is probably not quite as bad. The other thing they do very differently is they don't partition into lipids. So all the paradigms, how we understand PCBs and all these compounds, don't really work. They certainly bind to proteins, phospholipids. It's a very different mechanism, but unfortunately they still bioaccumulate. And so what we know now from various studies is basically they're everywhere. We know even at low concentration there are effects. Philippe Grandjean's probably famous paper on immunosuppression. There's several studies that show some link between the more P4 or PFAS you have in your blood or had in your mother when you were born, then that will lead to a higher chance of being overweight, having problem with insulin resistance or metabolic disorders. EPA took action through a voluntary agreement with manufacturers in the US that certainly helped get rid of PFAS and P4, which were the 2 main culprits at the time. But of course now we know that industry, to satisfy our needs for certain products, has just created a smorgasbord of all kinds of different compounds. And that makes life a little more complicated for the chemists among us. I know Graham makes his life easier because he can just detect everything, but he'll talk more about that later. There's a little sad twist to this, and the invention was, 80 years ago. The mass production started somewhere in the 50s, and it was banned around or withdrawn 2010 or so. The problem was that in between, both DuPont and 3M knew that it was present in their workers' blood. They realized it was getting out in the environment. They realized there were health effects. But at the time, both companies independently decided not to pass those information on to EPA, because I think DuPont claims to make $1 billion in profits a year, so that was probably a bit too much. So they were produced much longer than they should have been, because it could have been known that this wasn't a very good thing to keep those producing. The other thing we have learned about them was through happenstance, and that's Bob Billett, who was the lawyer who took on DuPont, and basically when he finally won in court to get a few millions, he used all that money to fund what might be the largest epi study ever for PFASs, the C8 study, and that has established links between high exposure and several kinds of cancer and so on. And it made DuPont settle for, I think was it $800 million? Apparently DuPont's stock was barely affected because they thought, oh, that was cheap. So anyhow, his work got him an honorary mention for the Nobel Peace Prize. And I'm glad he did that work. The other thing that, and that might have also got DuPont's attention at the time of 3M's, the problem is that this is for, I think, PFAS showing up in all kinds of animals. Not so much in the south, because luckily in the southern hemisphere fewer people live, so that's good news. But in the northern hemisphere they're present, and the top ones are seals and polar bears. So top predators, not a good thing. And if we look at some recent risk assessment or health index of these polar bears, and this is for cubs, this is work by Sarah Villa from Italy. So there's a health index here, that's the line, and you see over the last few decades the health index is going, or the hazard index is going down, so the animals are getting a little better. That's good news. Still too high, but nonetheless. But if you look at the breakdown, initially PCBs and DDTs were very important, and now you see the black bars, that's PFAS. So now a lot of the risk for the reproduction and well-being of polar bears is driven by the high levels of PFAS they have in their blood. So that's the sad news. And even though we banned their production a few years ago, because these animals live quite a long time, if everything goes well and they don't miss the shrinking ice, then you cannot do anything for the next few years because the body burden is just there. But the question remains then, why do polar bears are exposed to such high levels? So again, there's really only two ways you can get there. Either you come through the atmosphere or you come through the water. Now, I told you these compounds are ionic, and ionic chemicals don't travel well through the atmosphere, except there is a precursor there. The fluorothalonil alcohols, they are volatile. They are used in paints. They're used on kind of different coatings, so you'll find them in the wonderful, I guess, in our hotel rooms and probably on this carpet, because they have to be clean all the time. But they lose some of the chemicals every time. So indoor atmospheric concentration of fluorothalonil alcohols are fairly high, and once they get out, they can travel, and then over time they get oxidized. The moment they're oxidized, they probably start sticking either to a particle, to a raindrop, and then they're washed back out. So there's modeling effort that shows you have big plumes over North America, of course, Europe and China, and then those can indeed reach the Arctic. So there's an atmospheric pathway, indirect, and of course there's water mass transport. One of the first studies from a Japanese group was to show that indeed we find them in different parts of the oceans, and you even find them in the water masses going from the surface to form the new deep water, so they follow the water cycle. So what we then did is to ask colleagues who were going on a couple of cruises to collect samples for us. One was on the Polarstern, a German icebreaker, and the other was on an American ship, the Hilly. So the samples were taken were those in the central Arctic Ocean. Just to orient you, that's Greenland, Europe is somewhere here, Alaska is somewhere here, so it's a bit of a strange perspective. And the water coming in through the Atlantic would come in through this passage, as I said, and then would first reach this particular point and then slowly start moving around here. A quick word to the Arctic Ocean. There's a very well-mixed surface layer, polar mixed layer, that mixes within a year or so. Below that is is another layer, that's name I've forgotten now, that mixes on the timescale of decades or so. And then well below this, you have the deep Arctic water, and that is roughly hundreds of years old. So if the compounds just move through water mass transport, this layer should be completely clean, might be a little bit in this one, and the surface should be on the high side. So as I said, there were these 4 points where we got depth profiles, and this particular point here is the one that would be first reached by Atlantic ocean water, and that's this plot. And you see on the way is the polar mixed layer, and then you have the Atlantic water coming in here. And we indeed measure the first detection of several PFASs in this particular water mass, which would suggest that indeed it is slowly being pushed in from the Atlantic. And for all the other sites that are further away, we find nothing in the Atlantic water layer. Concentrations are on the order of tens of picograms per liter, so not particularly high, but through the accumulation of the food chain, that's sufficient to cause problems. We also then looked at stuff on the surface. So we looked at the surface ice, so the ice floats and slush, as in things that are starting to melt. Concentration are much higher, as another indication that indeed you have a transport through the atmosphere, and that gets captured by ice and snow and then reaches the surface. And they're order of hundreds to maybe 1,000 picograms per liter. And the last bit of evidence we used to figure out how important the ice or the atmospheric transport is. This is ratios of 2 of the PFASs from an ice cap where we only have atmospheric transport. And this is the same ratios for the surface water samples we had, and they all suggest indeed there's atmospheric transport. So, because we had now 4 sites, we thought that was enough to come up with a very crude but give you some idea of a mass balance for the Arctic. So this is in metric tons. And we see the ice contains maybe around 2 tons by now. The surface ocean or the surface Arctic layer maybe 30 tons, or quite a bit more. The marginal seas on the side, not as much. And the deep water, we didn't detect much, but it could be up to 10 tons, depending on how you use the detection limit. So maybe it's 50 tons or so, which doesn't really tell you that much. It's probably instructive to compare that to PCBs, and there's been a lot of work done by Swedish groups, and this is, even though it's small, I try to highlight the same numbers here. So PCBs in the ice, maybe 0.2 tons, so not very much. Surface layer, 2 tons. For PCBs, we think it's 30 for PFASs. The deep water, they have the biggest budget here of 30 tons or so, where we detect basically nothing. So there's 2 ways you can look at this. You can point out PCBs are much older, so they've had time to go down, they attach to particles, but there's still 30, 40 tons left of them, and PFASs are somewhat newer, and we already reached the same amount, same order of magnitude in the Arctic, so that's probably not a very good thing. What I think is going to happen is the Atlantic water will keep pushing in, and so the concentration of PFAS will start increasing because we get more and more into the Arctic Ocean. We see very little evidence that they bind to particles and settle down, and we see obviously both atmosphere and ocean play a role at this point. The nice thing is, because a lot of the water that comes from the Atlantic Ocean actually gets diverted and becomes deep water, so the Arctic is somewhat protected. It's not as bad as it could be. And the rest I'll skip. All right, well, you didn't, well, maybe you want to hear about ocean stuff, but I thought I'd actually come back close a little bit, just for a change. And I just want to highlight a very opportunistic study we did early on to look at PFASs in surface water. And we sampled across Rhode Island with a volunteer network. And because we're working at a Superfund site in the Passaic River, that's over here, so there's the Hudson and there's the Passaic, we thought, all right, Rhode Island is a very small state, as everybody knows and makes fun of. Very few people living there, hardly any industry, as our governor will attest, because we just don't do anything useful. And of course, New Jersey has this history of industrial proficiency and contaminating the countryside like crazy. So it was very clear where we're going to find high concentration of PFAS, right? It's going to be in New Jersey. Well, they're both on the same scale, and the highest bars are in Rhode Island. And that's both for the sulfonates and for the carboxylates. And that's caused quite a bit of head scratching, because it's against everything we know about pollutants. They scale normally with population. We looked at why could this be, and then if you go through the details, you find it could be, we do have an airport, and we have some textile production, We have wastewater treatment plants, and so on. So we have plenty of potential sources. But it was still a bit disconcerting that beautiful Rhode Island was just as bad as New Jersey. So then I was lucky to be involved in this study, and Simona was also part of this, to look at EPA-monitored data from the UCMR3. So that's when they look for unregulated contaminants across the US. Look for 6 compounds, I think, maybe it was 7. And they're only detected at a few sites, but enough to get some idea of what's happening. So the long-chain compounds are preferentially found in the groundwater. Shorter-chain compounds are more in the surface water. But then, what does it take to get PFAS in your water? And it turns out, if you like cooking, if you really want to get a lot of PFAS in your water, you follow this little guideline here, and that basically says, ideally you want to have a PFAS production facility, because that will really help you get something in the groundwater. If you want to do something else, then it would certainly help to have an airport nearby, because fire training certainly uses these compounds and they get into the groundwater. Wastewater treatment plant effluents also help, and that's because of the products we use in our houses, so then they get flushed through. So all of these will help you get a good level of PFAS. If you're not close to any of these, then either you're really lucky or you've got to move. And what else do we know? Roughly 6 million people are exposed at levels that are above what EPA considers safe at this point. We don't know anything about small public water supplies right now. We don't know anything about private wells. And there's a big question whether the EPA current advisory is sufficient. And that news has actually reached Washington, D.C., and I thought I'd just highlight a few of the things that have come up in the last few weeks and months. EPA had a very special summit because they realized PFAS are on everybody's agenda, so they had a national leadership did I just say shit? Excuse me. National Leadership Summit on PFAS, and that was not meant to be. But it's a great joke, I should have. And unfortunately, it turns out that nobody was invited to that event other than those that work in the agencies and industry. And there was also a new study underway from ATSDR that suggested maybe the levels that EPA has suggested at this point isn't safe enough, but it hasn't been released because it would have upset people. And also turns out that if you were a community group and exposed, you can't attend that summit because it wasn't meant for you. It also turns out you shouldn't go there and report about it because it wasn't meant for you either. But there was a good news. Senator Shaheen was able to secure, I think, $7 million for a PFAS health study linked to the, I think, Peace Air Force Base. So things are moving along. I think it'll take a lot of public push to convince EPA to reconsider what they've published so far. Because right now, EPA has not mandated drinking water guidelines. They have a health advisory, but the states have been a little more active. And all right, there's a small print. If you're New Jersey has been very active, so they've come around numbers around 10 nanograms per liter. Vermont is very similar. If you live in Texas, I guess because you're stronger built, you can take roughly 10 times that dose. New Jersey has by now issued 3 different advisories for PFOS, PFNA, PFOA, and for now, most serious advisories basically say PFOA and PFOS can be grouped together. EPA currently says 70. Most of the states come up, that's maybe 3 times lower. That might be closer to being safe. All right, so a few things what we're doing next. And the first one was mentioned. So I was leading an effort what we were able to successfully call a Superfund Research Center on PFAS. And shown here are 2 beautiful communities. This one on the Faroe Islands, where some of our epidemiological work is going on. And this is Cape Cod, which is just as beautiful, a little warmer, but had some recent exposure problems. So the center, as all of these Superfund centers need to have a combination of biomedical research. So we have, as I said, an epidemiological study on metabolic effects of PFAS and immune effects on the Faroes. So that's at background exposure. We have a matching into a targeted approach with rodents, in this case mice, on looking at metabolic effects. We have 2 on the environmental engineering side. One is transport and fate of these compounds in the groundwater from Elsie Sunderland from Harvard, and mine is looking at new detection tools for PFAS. And then complemented is the whole thing through community engagement on Cape Cod, research translation to our stakeholders, training of the graduate students, and just running the whole thing. I won't go into a lot of details, but you need a bunch of stakeholders that you can't read, but we have them. They're all hidden in this wonderful circle here. There's our science course, and there's our science project in the course. And this is probably on the science side more. This kind of highlights how we try to integrate the different projects, the epi in the field with the mice in the lab, the compounds we find in the field, how we bring it back to the lab. But we got only funded in September, so progress has been a little slow. But in case I ever come back, I can actually give you results. The other thing we're doing, this is not as well funded, but just as exciting, is a project that we started discussing a few years ago with Derek Muir from Environment Canada, is to see whether we can establish a global monitoring network for contaminants. And that is basically going on to field trials right now, looking at both coastal sites. These are these purple triangles. So we have a bunch of coastal sites across most of the continents, and a freshwater sampling program in blue across most of the continents. And the idea is to use the same kind of sampler, the same protocols, and actually also the same lab, and have deployments roughly at the same time. So to get a global map of different contaminants in fresh or coastal waters. And this is how this whole thing works. It's meant to be a network which is open to anybody who's interested in using it. If you have sufficient, if you have a defined idea, have some resources to get it going, then the people who deploy will happily to work with you. And we're going to look for a range of old compounds because we think we know what the results ought to be. And if those match our expectation, then we can use to new compounds, be that flame retardants or PFASs or microsystins, whatever it might be. And with that, I think I'm running out of time. So I started with some of the ocean work because I'm an oceanographer. That's kind of what I have to do sometimes. We see that the oceans have a lot of old compounds and new compounds. They fractionate as we had expected. We find there's a big import export business going around the Fram Strait, and still seems the atmosphere is much more important for moving compounds around than the water. On the PFAS side, at this point, it still looks as if, at least where we looked, that point sources are much more important than general background exposure. And it might be that EPA has to revisit the drinking water advisory, but that's, of course, a political question, so you have to ask the administrator. With that, thank you very much for your attention, and I'd be happy to take any questions.
So you have the old samples for measuring the PCBs from the ocean, right? Have you tried to relook at the PFAS in there? Or?
It's a good question. And no, because we are not sure that the way we handled samples in the past will be sufficient to make sure that we don't have a contamination problem now. And we do have blanks, but when we look for PCBs, DDTs, flame retardants, whatever, we use glass for sample handling, and then we use Teflon bottles for having our solvents. If we work with PFAS, we don't want glass and we don't want Teflon, so they're almost mutually exclusive. So that's why we haven't looked at those samples, because we're not sure that we have handled them properly at the time.
On one of your slides, you had a table with the different concentrations of PFAS, PFAS, and so on in the Arctic. And as you know, why do you think the shorter chain is at lower levels? They're more mobile, but is somehow associated with the production, or is there a difference in the transfer mechanism?
Wow, you read the small print. No, it's a good question. I assume, as I was saying, we think that atmospheric transport is still very important for a lot of the compounds we find. And I think the volatile precursors are biased towards producing hepta and octanoic acids. So I think that's why the shorter ones are not as present. I think if we look at the FTOHs, which would be the main precursor, it's mostly A2, 10-2, and 6-2 is a little less. That's my guess.